All right, so thank you very much. And first of all, let me thank Cody and John for putting up this very nice series of seminars together and for, of course, giving me the opportunity to present my work here. It's a real pleasure and I've enjoyed the rest of the seminars for the past few months. So it's very nice to have this opportunity. And so today I will be talking about two somewhat different topics, which are the first one is scale separation and the second one is this membrane potential correspondence. So the talk will be divided into two well-defined sections. The first one is basically based on this paper with Ana Maria Font and Luis Ibañez, and the second one on this other paper. So let me begin with the outline of the talk. So as I said, it has two parts. In the first one, which is about the scale separation in a particular class of type 2 orientifolds, I will try to basically first review this from the, very quickly recall the relevance of scale separation in the context of the swampland and in particular of the Antiseizure distance conjecture. And then I will try to present a couple of examples, a type 2A toroidal example and type 2B toroidal example, in which the main message will be the fact that is to emphasize the importance of the 10-dimensional picture when trying to address these issues of the scale separation in compactifications. And then, if time permits, in the second part of the talk, I will try to introduce this correspondence between the membranes, the interaction between membranes and the flux potential in 4 dimensions, in n=1 theories. So let me just begin with the first part, which is, as I said, this scale separation in a class of type 2A orientifold. So since this is a string pheno seminar talk, I won't really need to talk about I guess I don't really need to introduce the swampland. So let me very quickly go over it and say just that the swampland is the concept that appeared as opposed to the landscape, in the sense that not every effective field theory which looks consistent in lower dimensions can actually, or in lower energies, can actually be coupled to quantum gravity. And in fact, there is a huge set of effective field theories that look consistently from the IR perspective, but cannot be coupled to quantum gravity. And these are the ones that we call, we say that belong to the swampland. And the picture is a little bit like this, in the sense that we are trying to reach this, to find these spots in the space of effective field theories, which are the nice spots, the ones that belong to the landscape, but most of the effective field theories actually are more like this and cannot be coupled to quantum gravity and belong to the swampland. And the general question of the swampland program is, which are the generic features of all the effective field theories that arise from quantum gravity? Or said in a different way, which are the generic features that we have to demand for the effective field theories in order for them to be able to be coupled to quantum gravity? And these conditions are generally formulated in terms of these quantum gravity conjectures or swampland conjectures. We've heard about them several times. There are a lot of them. We have different regimes of applicability in the sense of constraining low energy physics, also different levels of rigor in trying to establish them. And basically, I will today focus on this Antiseizure distance conjecture here, because it is the relevant one to talk about scale separation. And I will try to first just recall what these conjectures say. So the issue of the scale separation in string theory in particular basically has to do with the fact of whether we can separate the typical energy scales of the compactification space and the external dimensions. And this has been ubiquitous in quantum gravity literature and string theory literature since a long time ago, as one can see from these references here. But it was revisited in the context of the swampland more recently by these people here. And actually last year, it turned into a more precise conjecture, the so-called Antiseizure distance conjecture by Lust, Palti, and Baffa, in which they basically proposed that in a theory of quantum gravity with a cosmological constant lambda, there should exist a tower of states that become light in the limit in which this lambda goes to 0. So basically, what they argue is that this lambda going to 0 is at infinite distance, and the mass of the states of the tower scales with this lambda to a positive power. In particular, the strong version of this conjecture, which is the one we'll be interested on today, says that this gamma must be equal to 1/2 for the supersymmetric case. And basically, what this implies is that if this tower is the KK tower, which is the typical thing, at least in all the examples that we will study here, what this coefficient gamma being equals to 1/2 implies is that there is actually no scale separation, because basically one can calculate, if one associates the typical internal scale to the KK mass, and one calculates the typical external scale by obtained from the cosmological constant, what this gamma equals to 1/2 means that the internal radius is proportional to the external radius. So basically, with gamma equals to 1/2 and this tower being the KK tower, the ADS distance conjecture implies that we cannot have a scale separation. And in particular, as I was saying, this is very crucial for this problem, and it's actually very important in trying to make some phenomenological models or describing the real world, because, for example, scale separation is a critical issue for uplifting mechanisms. So basically, we generally need to have scale separated vacua when we're trying to uplift some vacuum to the seeds or something like that. But just per se, this is a very interesting problem, and I'm trying to address it in these particularly simple examples came from type 2A orientifolds. Well, first type 2A, then type 2B. So the idea here is the playground that we will be using in this case is, as I was saying, type 2A toroidal orientifolds. In particular, I will take an isotropic type 2A toroidal orientifold, so that the moduli that we have are these three, just an STU model, in the sense that we have these T's, which are the Kähler moduli, these U, which are the complex structure moduli, and this S, which includes the 10D dilaton, and both of them are in the n=1 complex structure sector. And on top of that, on top of this toroidal orientifold, we will put some fluxes. So the typical thing, the customary thing, is to put these Ramon fluxes and NS fluxes that we will denote like this. How this works in order to look for vacua is these fluxes generate a perturbative superpotential, which in type 2A actually generates this superpotential for all the moduli, so it allows to fix all the moduli. There's the crucial constraint coming from tadpole cancellation from the C7 tadpole, which includes this part here, which has to do with this F0 flux and this class which depends on the H3 flux, and then the contribution from localized sources, namely O planes and D branes, D6 branes here. But this has been studied, and these are the very well-known called now DGKP vacua, which seem to exhibit a scale separation. There are also a similar family of them by Cámara, Fontana, Ibáñez about the same time, which and the thing here is there exists this vacua from the 4D effective field theory point of view, which is given by this superpotential, and they seem to be scale separated, to exhibit a scale separation. They are supersymmetric, so they would seem to contradict the Antiseizure distance conjecture. But what the authors of the ADC argued was that maybe there was some problem with the uplift to 10 dimensions. This issue has been revisited in this context lately by Jungans and Marchesano, Palti, Kiranta, Tomasiello, like trying to make this 10D picture, this 10D construction more precise. And there's definitely progress in that direction. It was also revisited by Burgatti, Calderon, Minino, and Uranga by refining the conjecture. But what I'm going to try to do here is, instead of reviewing this particular model, which has a lot of technical issues, and most of them are not completely settled yet, I think, I will try to review a very similar, closely related causing of this model, in which what I will try to emphasize is that what seems to be a scale separation from the naive 4-dimensional point of view turns out not to be a scale separation when we take this 10D picture into account. So what I'm going to consider is this model, in which apart from these fluxes, in this isotropic type 2A toroidal orientifold, the same one I was talking about, but with these extra fluxes, these metric fluxes, which basically can be seen as contributing from the 10D picture as contributing to the globally defined basis of one forms in this parent torus. At the effective field theory level, what these guys do is just to give extra terms in the superpotential, these two terms here. They also give an extra contribution to the tadpoles, so that what we can do if we have a Romance mass, this M here different from 0, is to cancel the localized sources among themselves. So O6 planes with D6 rains on top, and we forget about that, and we can cancel the fluxes among themselves too. And from the effective field theory point of view, we just put these fluxes on top of the toroidal orientifold, and what happens is that we minimize the potential and we obtain some supersymmetric ADS vacua. These were found here. Everything seems to be fine with them. They are supersymmetric, as I said. They depend on the fluxes that we are putting. Very importantly, these fluxes are unconstrained by tadpoles, because we've already substituted this. We've solved explicitly these tadpoles by writing H and H0 in terms of the rest of the fluxes. And what one finds is that this quotient, which is the relevant one to study scale separation, has the following behavior in terms of the fluxes. So basically, this is the quotient which is relevant because it has the 1/2 here, and it goes like 1 over these fluxes AF cubed to the 1/4. And now the thing is that one could say, okay, since these fluxes are unconstrained by tadpoles because they are already substituted there, one could try to make them very big, and it turns out this quotient goes to 0. So it seems not to fulfill the anti-de Sitter distance conjecture, because this should be equal to 1 in that limit, because this is the limit also in which how is this? Yes, sorry. So this is, sorry, so this is the limit in which this goes to 0. Now, one could argue that basically this is telling you that this is inverse scale separation, because it has the opposite behavior to what one would expect to be a scale separation. So it's like the internal scale becoming much bigger than the external scale, but still it's a departure from the behavior that one would expect from the anti-de Sitter distance conjecture. Now, what happens is that in fact, we are neglecting something here, and from the naive EFT point of view, we are neglecting the back reaction of these fluxes that we've turned on in the 10-dimensional geometry. And in particular, these kind of solutions are known. They were studied by all these people, and in particular, in this paper, it was found that with this particular set of fluxes, there's a 10D uplift of this configuration of fluxes, which corresponds to well, this should be ADS4 cross S3 cross S3. But the key ingredient is that when one includes all this, there's one crucial change that we were not detecting at the 4-dimensional EFT level, which is the fact that the volume of the internal manifold is corrected by this thing here, because this is the T cubed, which is the characteristic volume of the torus. We have the toroidal compactification. We estimate the volume by T to the cubed. That's what one obtains from the toroidal picture. But there's this crucial value here, which is flux dependent, which depends on these fluxes in this way. And in particular, this correction propagates to the superpotential and the Kähler potential. And at the end of the day, what it does is to appear here and here. And in the quotient, it appears like this. And what this is, when you substitute this here, what you obtain is that this quotient is actually flux independent, and the ADCs will fit. So basically, the message here is that from the naive EFT point of view, not including the 10D equations of motion and not including the back reaction, we were not detecting this correction here, which turns out to be crucial for the study of scale separation. Now, it is true that, as I was saying, this is not real scale separation, because it's the opposite if you want. So let me very quickly introduce a type 2B modeling, which from the EFT point of view, it looks like there is a scale separation. It requires non-geometric fluxes. So this is the dual of one of these type 2A models that I was talking about. To obtain the superpotential, one can just do T-duality and exchange U's and T's and keeps the S's in the same way. But the key point is that here we have this vacuum. There's a supersymmetric ATS vacuum with this behavior, with this dependence on the fluxes, and the quotient between these two guys goes like this. And actually, E0 is not constrained by tadpoles, so now one can make this E0 go to infinity, then this thing goes to infinity, and we seem to have a scale separation. Now, this is a non-geometric thing, and we are estimating the radius of the internal manifold again as the volume of the torus, of the internal torus. But the key point here is, okay, this is non-geometric. We don't really know how to go to the 10D picture, let's say. But as I was saying, this is T-dual to one of the type 2A cases I was talking about right before. Not the same example I was showing, but one without the Romance mass. Actually, this M here is 0. But the key is that to go from this type 2A to type 2B, what one does is to perform 3 T-dualities along these X directions. Let's call X directions of the torus. But the key point with this is that the scale associated to the Y directions is untouched upon these 3 T-dualities. So basically what we can do is go to the type 2A dual, estimate the typical size associated to the Y directions, and from there, this size should not change when we go to the type 2B picture. And then we can estimate that way the KK scales from the type 2, the correct type 2B KK scales in the type 2B picture from the fully backreacted solution in type 2A. And what happens is that when one does that, actually, again, this is corrected and these guys are corrected as well in such a way that once again, this thing that now seemed to be like a scale separation is not a scale separation anymore. And we have this quotient which is flux independent, and we again fulfill the anti-de Sitter distance conjecture. So this is the first part of the talk. So in this remaining a bit more than 5 minutes that I think I have, I will try to go to the second. But before going there, let me just emphasize that the only message that I want to convey here with these two very simple models is the fact that there has been a lot of claims on scale separation or no scale separation regarded on purely for the effective field theory information, but one has to be really careful on how to identify this for the effective field theory, and in particular for issues which are about scale separation, which is an intrinsically 10-dimensional thing. One should definitely know the 10-dimensional picture well before doing any claim. So this being said, let me go to the second part of the talk, and this relation between membranes and the flux potential, or the n=1 extern potential, if you want. So before going into the details, let me very quickly recall a couple of things about free forms and membranes in 4 dimensions, because I think more people are familiar with the n=1 scalar potential in general, but maybe not so many people are familiar with free forms in 4 dimensions. So just let me begin by introducing a 3 form in 4 dimensions, and the typical action that describes this 3 form is of this form, basically, where we have these kinetic terms, which are just with the 4-form field strength squared, the natural coupling of 3 forms to membranes with charge Q. When I'm saying membranes, let me recall that I mean codimension 1 objects in 4 dimensions. So this is the action. There are some boundary terms that I will not discuss. They are crucial for the variational problem to be well defined asymptotically and so on, but they are not important for this discussion. The key point is that the equation of motion away from the membranes has the following form. So this means that there is no propagating degree of freedom in the 3 forms, but still they can have some non-vanishing value for F0. So they can have some constant non-zero value. And in fact, when we plug this back into the action, what we can get is a contribution to the cosmological constant. So basically 4 forms do not propagate degrees of freedom by themselves, but they can contribute to the cosmological constant. And in particular, the memories to which they couple separate different vacua with different values of this cosmological constant. And in fact, this change in the cosmological constant when crossing a membrane is given by the charge of this membrane. Okay, so at this level, this Q is just some undetermined parameters that we're putting here, but the important point is that it gives the difference between the cosmological constant at both sides. Now, the important thing here is that these four forms are not only able to encode this cosmological constant, but in fact, they can encode more complicated potentials. And a typical example is the Caloper servo, dually Caloper servo mechanism to include a potential for an axion with a shift symmetry. But this can be generalized to more complicated setups. And in fact, for example, for type 2A flux compactifications with the fluxes I was introducing before, there is this structure for the four-dimensional effective action, which includes the kinetic term for the four forms, and this coupling with these Qs, which are the fluxes in the compactification. If you want, one can do the same. One can integrate out these four forms by using their equations of motion. But the important point is that, again, as before, the cosmological constant was given by some quadratic, this F0 that we were talking about squared. Now the potential, more complicated potentials can be written in this way, which are quadratic in these fluxes of the compactifications, and with this set, which is a field-dependent matrix, and includes the potential for basically that's what encodes the potential for the fields, which is just the inverse of the kinetic terms of the four forms. Now, in these setups, like for example, I was saying type 2A orientifold compactifications, these are n=1 flux compactifications, and we also have the usual Kremer et al. Formula for the potential in terms of the superpotential and the Kähler potential. This is well known, probably everyone knows how this works. But the key thing here is that we have these two ways of expressing the potential, and both of them are quadratic in some object. In particular, this is quadratic in these charges, and this is quadratic in the superpotential or quadratic in the covariant derivatives, if you want. So it somehow resembles the structure of an interaction between two objects. And the idea here is, okay, so we have these two ways of writing this potential. So is there any way to interpret all these contributions, this contribution here, this contribution here, and this contribution here to the scalar potential in terms of interactions between membranes, which source the corresponding fluxes? In order to do that, we can consider two parallel BPS membranes, which are available in n=1. Their tension is fixed by supersymmetry. This is given by this thing here in terms of the superpotential and the Kähler potential. And what we can do is to try to consider two membranes which source the whole potential. So basically, this is like in this picture that I was showing here. Imagine we have 0 fluxes on one side of the brain, and then all the fluxes are sourced by the charge of the membrane. So if we consider this, the interactions between these two membranes due to gravitons, scalar fields, and free forms, to which they naturally couple, as I was saying before, can be encoded at the linearized level in the following Feynman diagrams, if you want. These Feynman diagrams, we have all the information that we need to calculate the amplitudes corresponding to this Feynman diagram. So basically, we can calculate this vertex between the scalar and the membrane from this part of the action, because as we said before, the tension depends on the superpotential and the Kähler potential, so it depends on the fields. Through here, we can calculate the propagator for the scalar from its kinetic terms. The same for the three form, we can calculate the vertex from the coupling, the natural coupling between the three form and the membrane world volume. We can calculate the propagator of the three form from its kinetic term from this AB, and the same for the graviton. We can calculate it, the vertex from the expansion of this of the square root here, and the propagator from the Einstein-Hilbert term. And what one obtains when one does this calculation is that these amplitudes are proportional to the following, to these three quantities here. Now, of course, there is a dependence with the distance. In fact, the forces are constant; they do not depend on the distance. From the amplitudes, one can calculate the potential, which grows linearly. But the key is that all that can be factorized, and the strength of these interactions is given by these three things. So basically, the scalar exchange can be mapped to this part here, the graviton exchange to this part here and the free-form interaction to this part here. So the thing is that we have a picture in which we have the scalar potential, and we can talk about vacua and minima of the potential, or points in different points in field space with different potential for the fields. And there seems to be another picture to think about this, in which we can think of it as interactions between the membranes. And for example, in this respect, a supersymmetric vacuum, which corresponds to this DIW equals to 0, would correspond to a configuration in which we have no interaction between membranes, no scalar interaction, sorry, between the membranes. Or Minkowski vacuum would mean no free-form interaction between membranes. And the most interesting consequence of this, I think, or like one of the most promising things that one can try to do with this, is to relate conjectures about the objects, these membranes, which relate the charges or the tensions of these membranes, with conjectures about the scalar potential that they generate. And in fact, using similar arguments and the version of the weak gravity conjecture for membranes, Lanza, Marchesano, Martucci, and Valenzuela were able to prove an asymptotic version of the de Sitter conjecture as a consequence of the weak gravity conjecture for membranes. So this correspondence seems to give a nice way to connect these two things. So I think I'm a bit over time, so I will just stop here and just let me remark these two things. That the first one, the first part, that this correction from the internal back reaction, at least in this class of models, is crucial to study scale separation. So one could think that definitely the naively obtained results from the EFT are not enough. And the second, that there's this equivalence between these two pictures, the potential and the membranes interaction, that could lead to relations between these conjectures. So that's it. Thank you very much.
All right, thank you, Alvaro, for the very nice talk. Let's all thank Alvaro with our clap emojis. Are there any questions? While we wait, can you just, I don't think I completely caught this. Can you just say again on the type 2B side, how you were arguing for the no scale separation, in particular the KK scale?
Sure. Yeah, so the idea is the following. So this type 2B model with non-geometric fluxes is dual to a type 2A model in which all fluxes are geometric. Okay, and the way in which you go from one to the other is, it's not exactly the same model as I was showing before, but it's closely related. So we know the 10D picture, and the way you go from one to another is just by performing three T-dualities in the parent torus, let's say, in this toroidal compactification. So these three T-dualities go along the three, let's say, x directions. So basically they change the sizes of the x directions, whatever, but they do not touch the y directions. Okay, so basically what I'm saying is we can go to the type 2A picture. The size, the distances associated to the y directions are the same in both compactifications, and in one of them I know the 10D picture in the type 2A thing. So I will calculate the KK scale, or the typical length scale associated to that, in the type 2A picture, and then when I go to the type 2B picture, that shouldn't change at all. So that's how I calculate the type 2B KK scale, by declaring that it is equal to the one in the type 2A case in the directions that I'm not T-dualizing.
Okay, thank you.
Okay.
If there are no further questions, let's thank Alvaro one more time.